Hello, I am going to be going over a simplified weld analysis problem. So here we have this problem right here. We have that we see that the weld callout is a nearsighted weld, and that it is defined with the circle here. This basically means that it is an all-around weld. So the arrow points directly here, so this is going to get a weld. Since it's an all-around weld, it's going to go down, right, and behind the bar. These dashed lines represent the weld being having to be welded behind the surface. So if you picture this in 3 dimensions, you're able to see that this bar is in the bottom of this bar, so the weld's going to go to the back. So here we have this force pushing the bar in the left direction. So moving on, let's read out our problem statement. So what is given? A steel bar of thickness h equals 5/16 inches and dimension b equals 4 inches, c 7 inches, d 4 inches is welded to a vertical support as shown. Find. Determine the maximum force P that can be determined if the weld allowable is 16 KSI. So to start off with, step number 1, find the area of the weld. So from the callout, we see that the weld is an all-around weld. So it is also a box weld. And also it is in plane because we have this force in the x direction. So here, looking at our handbook, we can refer to the equation for area as being 1.414 h b plus d. Here I went ahead and did the calculations for you guys. So we get an area of 3.535 inches squared using the box method approach for simple weld analysis. Step 2, find the torsional parameter Ju. This can also be found in that same row for the table provided by the handbook. So Ju, I like to think about it as some sort of conditional or temporary torsional constant. So Ju is going to be equal to b plus d cubed divided by 6. I went ahead and did the calculations again, and we got 85.33 inches to the 4th. Moving on, since this is the temporary or conditional torsional parameter, we have to go ahead and find the actual torsion constant J. This is going to be given by 0.707, the dimension of the weld, times the torsional parameter. So here, did the calculations, and we got 18.85 inches to the 4th. Next, it is important that we define our H and Y bar. These equations can be found in the table as well for in-plane simple weld analysis. So we get an X bar of 2 inches and a Y bar of 2 inches as well. Here it's square, so we could, and the dimensions are the same, so we can see that the X bar and Y bar are going to be at 2 inches each. Moving on to finding the moment produced by that force at the centroid, we're going to see that the equation is given by mc minus px, y load minus y bar, plus py, x load minus x bar. So here we do not have a moment in the z direction initially, so that can be crossed out. And there is no y load, so that can be crossed out as well. So here we have minus px, y load minus y bar. Remember, always carry your signs too. So I went ahead and wrote it here. Here is that negative. And since the direction is going to the left, we're going to define it as minus px here. So now the y load is going to simply be the y direction going up. So that's going to be d for that p. So it's going to be 4. So here we have minus, which is going to create a positive moment, 2px. So here, to find the shear stress at any point in the weld, it's going to be given by these equations here. Remember, take note, it's negative here, a positive here. Here, this equation just finds the magnitude between the 2 shear stresses in each direction. So it is important that we consider every single point in a weld, but for this equation and problem, we're going to be using a point that is located in the top right, because once you do so many problems, you get to notice that the critical point, if the load is here, if we have a load in the y direction or in the x direction, or even a moment at times, we can see that the critical point is the top right. So here, for the purpose of this example, we're going to be analyzing the top right. So using the equations from above, we're going to go ahead and find the shear stress in the x direction. So here we have a negative force, so it's going to be defined with a negative. Here we have the sum of the moment of the weld, the sum of the area of the weld for a box weld is 3.535, which we calculated above, minus, do not forget your signs, common student error. And then we have our positive moment that we got from up here. And then we're going to go ahead and also do the direction or placement of the weld that we are looking at here. So since we are looking at the top right, we're going to be using this x and y value if we define our coordinate system from the bottom left. So here it's going to be 4 minus our y bar, which is 2 inches, divided by the torsional constant, the actual torsional constant. Here we get a value of negative 0.495 px. Again, moving on, we're going to analyze the shear stress in the y direction. Here, we do not have a y load, so it's going to be 0 for py. So this term is just going to go to 0. Then we have our moment again. It comes up again, so it's 2px. We have the location of the weld at the top right, which is 4 inches in the x direction. So here it's minus the 2 inches being the x bar divided by the torsional constant. So here we get that the stress in the y direction is given by 0.2122 px. So here we're going to find the magnitude of that by squaring both x and y terms. We get a value of 0.53 and a few other numbers after that. I just did 0.53 for simplicity. So going ahead and plugging in our tau r is going to be the allowable, which is 16 ksi. We went ahead and did that. And then to cancel out the square root here, we're going to square this left side. So 16 squared is 256. And then we're going to go ahead and divide this thing over here. We get 475.26. And again, we have more decimals here, but I went ahead and wrote it like this for concision. So here we just get this value here. We isolate px to find the max stress. So we just take the square root of this side and this side, and we get that the max force is going to be 21.8 kips. So in summary, we went ahead and determined the max force that can be applied if the weld allowable is 16 ksi. From the callout, we were able to see that the weld is a box weld, denoted by the all around, and the nearsighted well callout. Here are the dimensions. We went ahead and did step number 1, which is find the area. Step number 2, we found the conditional parameter Ju. Step 3, we found the actual torsional constant. These equations are all provided in the handbook. We went ahead and found the xy, the x bar and y bar, and the moment caused by that eccentric load. mz 2px, x bar, y bar 2 inches. Then we went ahead and found the shear stress and the x and y direction given by the equations here. Remember, signs are important. Don't forget them. So in theory, we always consider each point on a weld, but for this example, we went ahead and considered the critical point. So this was the top right. We went ahead and found the shear stress in the x direction, shear stress in the y direction. We went ahead and did the magnitude. And for this problem specifically, we wanted to find the maximum force for the allowable of 16 ksi. So we went ahead and just equaled the left side to the allowable, and we found that the max force was 21.8 kips. That's it. Easy stuff. Just practice and practice. Practice makes perfect. Enjoy.